let's look at some of the technical details of how Zscaler's bandwidth control works. As you could see from an end user perspective, users go to all type of destinations or applications and activity over the internet. So people go to CNN or any other news media portals. They go to YouTube to watch videos. They even access Salesforce, Workday, and other SaaS services. The same internet connectivity is leveraged for accessing sometimes social media applications, online gaming, and also it is leveraged for connecting to Microsoft 365 type of services like Exchange Online, Outlook Online, and even Gmail, OneDrive, and other types of services. So what Zscaler does is it uses a fine-tuned algorithm which allows the full utilization of bandwidth unless there is a contention. So by default, the available bandwidth from or which is coming to Zscaler Edge on the Zscaler enforcement node assumes that it needs to use all the available bandwidth unless it is defined through a policy or configured through a policy how to resolve the contention between those applications. So that's the default behavior. And once a quota is reached, packets are buffered. So all the transactions to internet, 99% of them, or even 99.9% of them are HTTP and HTTPS based transactions, more of HTTPS SSL based connections. So when the TCP session is initiated from these end users through the locations connected to Zscaler data centers, Zscaler terminates that TCP connection. Zscaler does man in the middle for these connections. So when the TCP is terminated and handled by Zscaler enforcement node, we have the ability to play with different options of TCP, adjusting the bandwidth window sizing, the TCP window sizing, buffering, and so on and so forth. So the technique Zscaler uses for all the internet-based transactions is more of a shaping and buffering technology as opposed to packet dropping and policing technologies, which you would see on a physical hardware-based quality of service capability from on-prem appliances. Now, the other thing is since Zscaler does a TCP proxy or handles the TCP connection of user for every session, we have the ability to slow down the applications using TCP window size, as I mentioned, and other techniques to provide appropriate buffers and manage those sessions in a much effective way to guarantee the bandwidth prioritization and services for end applications. And also, we do rebalancing bandwidth every 1 second if multiple rules are defined. This is very important to make sure as the applications start coming, you already have existing sessions in flight. So this rebalancing becomes very critical, and the duration we take to rebalance has an impact on how many buffers we use and how we are guaranteeing that bandwidth for a particular SaaS application. In summary, Zscaler uses a shaping and buffering technology of all the TCP connections coming onto Zscaler enforcement node to provide the guaranteed services related to bandwidth when it comes to managing application bandwidth prioritization and control. Now, let's look at some of the details to understand how policing and shaping are different, because Zscaler uses a shaping and buffering technology as opposed to policing approach. So if you look at policing, typically when traffic arrives at the edge, so it gets classified what application it is. And once the classification is done, in a policer approach, packets simply get dropped. And as soon as the traffic exceeds certain limit of threshold which is set, the approach in policing is to simply drop the packet. And this is mostly used as a capability to rate limit, where you have an endpoint which is generating multiple gigs of traffic so that you just smooth out the traffic by dropping the packets. And oftentimes, direction in which you apply shape in policing is both inbound and outbound. Since it acts as a pure rate limiting function, it acts in both bidirectional aspects. And especially the value from policing is more when you see a spike of burst or some anomalous traffic burst happening or transmitted. So the expected results when such a burst traffic happens is you get smoothed out. That means you drop all the excess packets which are going certain threshold and you smooth the traffic out. And from a TCP behavior perspective, the drops cause TCP retransmissions, and you would effectively see things like your YouTube video would be doing resets, or you would see some choppiness in the video, pauses, and so on and so forth. And there is no queuing performed in policing. It's strictly amount of packets, whether they're hitting certain threshold, you drop it or not. It is very commonly used in applications which are more delay sensitive, like UDP, streaming media, voice, video, where dropping few packets would not really make much difference to the application. Whereas when it comes to internet, most of the applications, as I said, is TCP based or SSL based. It is important to not lose or sacrifice the user experience aspect of those application access. So the way we do that is by providing additional buffers per session. And we delay those existing sessions or store the applications based on the configuration by putting those packets in buffers. That means you're not dropping the packets. And since the nature of the traffic is always going out towards internet, it is outbound in nature. And this guarantees you and smoothens out the traffic. And even if there is bursts of traffic, you simply see a smoothness in the traffic, especially in the example of YouTube. The same situation, the way Shaping handles is by throwing additional buffers, it smoothens out. It drops down from higher 720p to 480p type of resolution as part of that smoothness, and effectively customer or end user would not see much impact. As I said, queuing is performed with high memory buffers. So you have enough buffers and memory available for providing this bandwidth control capability in Zscaler enforcement nodes. Also, it is commonly used for delay insensitive traffic or any web traffic, particularly where dropping the packets is not an option.